Question 7. You have won the lottery. You have a choice. You can receive 5.5 million today, or you can get 40 payments of 1.9 million starting a year from now, but paid every 6 months. So this is going to be tricky because it's an annuity, but the present value won't be, you can't do it today. You have to do the present value of the annuity starting 6 months from now. But we'll get to that in a second. So your other option is you get 35 million. If the appropriate discount rate is 9% compounded daily, should you take the offer, assume there are 12 months in a year and each has 30 days. So it's going to be 360 to get the proper APR, but we'll get there. So I've already worked it, but let me work it again from start to finish so that you guys can see. Okay, step 1, APR, 9%, 0.09. Oops. Let's get the effective daily rate. The reason that we're doing this wrap text is because it's compounded daily, and therefore we need to convert from the daily rate to whatever other rate we need. Normally I would do 365, but the assumption on this is that a year is composed of 12 months and that each of those have 30 days, and that will give you 360. So notice the second thing is we've divided once, we got the effective daily rate. Let's forget that the APR ever existed. Okay, so the payments occur every 6 months. The easiest way to do this is to do the effective semi-annual rate. So this would be if what would your balance be of $1? If you had $1 balance on your credit card and it compounded every day for 6 months, how much would you owe at the end of that time period? So let's do 1 plus that to the power of 30 times 6 months. 4.6%. Okay, now we have our interest rate. Let's do option 1. And I'm going to, now that I've learned a little bit about how to set up this project, I'm going to move this. Okay, so the first thing is the payments occur every 6 months after the initial payment. So I'm going to put time right here. Well, let's move it down. 0, 1, 2, 3 equals that plus 1. Now notice that since time is every 6 months, this is half a year. This is 1 year, it's 1.5 years, 2 years, so this is going to equal that plus 0.5. Okay, this is just for my own record keeping. Let's fill in the cash flows and then I'll explain this. Actually equals that works. Okay. So notice that we have 1.9 million and we get 40 payments of it, but they start 1 year from now and will be paid every 6 months. So what happens is we get $0 when we're at time 1, which is 6 months, because our timeline we had to adjust for these new payments. We have the annual rate, the effective semi-annual rate, and all we have to do is work backwards now to get the present value, but we have to fill in the correct number of payments. So we need this number on the annuity to equal 40 because there are 40 payments. Oh, look at that, I did it almost perfectly. Okay, so at time 41, at 41 6-month intervals in, or 20.5 years into the project, or into the lottery payment, I get my final payment for 1.9 million. So the only thing that's left here, the last thing that's left is to take the present value of the cash flows and then to get the NPV by summing them. This is the same exact formula that we have used from the beginning of the class. Okay, 38,442,698 is the answer. And the other offer was 35 million, so let me write option 2 out here. One more zero. Notice that the NPV on this project is higher than the NPV on that project, or on that offer, and so we're going to keep the annuity, or this lottery payment. We're going to keep our rights to the stream of lottery payments. Now, you'll notice that this is an annuity. There is another way to do this, and so let me just add a column in here. Okay, so if this was an annuity, the present value of the annuity would be standing right here. Let me make it bold. So, like, remember off to this, here, let me do it off to the side. So when we had this annuity, when I told you in class, you would have some cash flow, C, and the value of the annuity would be PV standing here. Let me wrap the text. So you're standing in time 0, you get it in the next time period. So you can value this as an annuity, but notice that you'll be standing in time 1. So we could do NPV, the rate is the effective annual rate, but you have to subtract 1 because it's not in percent terms, it's in 1.0 whatever. And then, actually, I think you do PV. That minus 1. Yeah, you're right. Number of periods is 40 because we're going to have 40 payments. The payment is this, but remember we have to put a negative because Excel does that weird thing. There's no future value and there's no type. We're just going to close the parentheses. And we get 34 million and that. But notice that it's not in present value terms. It's in value at time 1. So in order to get the present value, in this example, let's do... I'm going to make this whole thing a different color. Your cash flow, let's add some borders here so we can see what we're doing. You're going to have a $5.5 million cash flow. So you have an annuity whose present value at time 1 is 34 and change, and then you have a cash flow that's here. We take the present value of the cash flow, just like we did on the other one, Command T to the power of 0. That's a little bit hard to read. And then if we get the NPV, which is just equals that plus that, we got the same thing. So let me make it, yay. These are the same numbers. And we did it in 2 different ways. In this way, we took the NPV of all of the cash flows, and we just drew a timeline the whole way. And in this one, we took the NPV of an annuity, but we made sure that we did it at the correct time period. So in this case, we're standing at time 0, looking 1 period forward, and that is the value of the NPV if you're standing 6 months in. When you do that, you have to discount it back, add them up, and then you get the total NPV.